Linear programming, graphical methods. In any linear programming problem, we seek the point or points in the region determined by the constraint inequalities that give optimal, which could be maximum or minimum, values for the objective function, which is the function we seek to optimize. Any point in the region determined by the constraints is called a feasible solution to the linear programming problem, and the region itself is called the feasible region. Here we have in example 1, an example of finding optimal values of a function subject to constraints. These are the constraints, and we are defining the maximum value and the minimum value of c equals 5x plus 3y. First off, let's modify these inequalities so that they're in a form that we can put in our equation editor. So y less than equal to 5 minus x, and y less than equal to 8 minus 2x. You don't have to graph x greater than equal to 0 and y greater than equal to 0. What this does is limits you to the first quadrant of the graphing calculator. So you can just limit the window to the first quadrant and then look at where these two functions will overlap regions. So let's go to the equation editor and put 5 minus x, and let's go back in on the line there. We can open that menu and change the shading. Of course, we want y less than, so we're going to shade below. The other one's also below. Since we're there, we'll go ahead and change it to, and that was 8 minus 2x. All right, let's set our window. Let's make a x minimum of 0 and a y minimum of 0 and just see what kind of a graph we come up with. And you do see the region there that is the feasible region. Any point that is in that double shaded area is going to be a viable solution for this problem. Will satisfy the constraints that were given. If we want to optimize this, then those points that make the corner of that region, the corners of the region, will be what maximizes or minimizes the objective function c equals 5x plus 3y. So our job is to find the points. Let's find the intersection between those two boundary points. We get the point 3, 2. And we can also find the 0. We want the 0 not of the blue function but of the red, so left bound, right bound, and we get 4, 0. And let's find this point. We can just trace and make sure that you're on the blue function. Enter 0, you get 0, 5. And we know that this is the point 0, 0 because of our window settings and also because of the x and y intercepts that we found above. Let's go ahead and put this into the function that we are supposed to optimize. So it'll be 5 times the x value plus 3 times the y value. So that's 15 plus 6, which is 21. 5 times 4 plus 3 times 0 is going to be 20. 5 times 0 plus 3 times 5 is 15. And 5 times 0 plus 3 times 0 is 0. So this is going to be the maximum, and this is going to be the minimum. Example 2 is cost minimization. Star Manufacturing Company produces two types of Blu-ray players, which are assembled at two different locations. Plant 1 can assemble 60 units of the Star model and 80 units of the Pro Star model per hour, and Plant 2 can assemble 300 units of the Star model and 80 units of the Pro Star model per hour. The company needs to produce at least 5,400 units of the Star model and at least 4,000 units of the Pro Star model to fill an order. If it costs $2,000 per hour to run Plant 1 and $3,000 per hour to run Plant 2, how many hours should each plant spend on manufacturing Blu-ray players to minimize its cost for this order? And what is the minimum cost for the order? The first thing that we want to do is to identify what our variables are going to represent. Okay? The thing that they are asking is how many hours should each plant spend on manufacturing the Blu-ray players. So let's let X equal the number of hours that Plant 1 operates, and Y equal the number of hours that Plant 2 operates. Now that we have those variables defined, we can start on our constraints. Look at things like the company needs to produce at least 5,400 units of the Star model and 4,000 units of the Pro Star, and that's again at least 4,000 units of that Pro Star model to fill the order. Those sound like conditions that we need, some threshold, and that is the type of language you're looking for. The at least, we know that that's going to be part of our set of constraints. So if we are looking at least 5,400 units of the Star model, let's see what kind of an equation we can make with that. How many units of the Star model is the Plant 1 going to make? So we come back up here. Plant 1 can assemble 60 units of the Star model. Okay, 60 units of the Star model. And so if they, and that's per hour, so if they operate for 1 hour, it'd be 1 times 60. If they operate for 2 hours, it'd be 2 times 60 units. If they operate for 3 hours, it would be 3 times 60 units, and so on. If they're operating X number of hours, then they will be making 60 times X units of the Star model. And the other company, the other factory is going to make 300 of the Star model. So, and that's every hour. So they're going to take and make 300 Star model Blu-ray players times every hour that they are opened. So you can think of this as our Star inequality. That is the Star model, and we need to make at least 5,400 units. So it means 5,400 is the least number of units we can make. If we make more than that, then that's also a good thing. Now let's make an inequality with our Pro Star. Our Pro Star model going on here. Let's see, I have 80 units of the Pro Star from Plant 1. So they're going to be 80 times however many hours they operate. And we can add that to 80 units of the Pro Star model per hour for the second plant. So that'd be 80 times however many hours they operate. And they need to make at least, again, at least 4,000 units of the Pro Star model. So greater than or equal to 4,000 units. The thing that we're going to want to optimize is the cost. In this case, we're minimizing the cost. So let's come up with an equation, a cost equation that we can optimize. So this is our objective function. The cost is going to be cost $2,000 per hour to run plant 1. So that would be 2,000 times however many hours they operate. That would be the cost for running plant 1. And $3,000 per hour to run plant 2. So that would be 3,000 times however many hours plant 2 operates. Okay, it also goes that we're going to be operating plant 1 and plant 2 greater than or equal to 0 hours. We're going to operate these two factories, these two locations, a positive number of hours or 0 hours. We can't operate them a negative number of hours. So this is our set of constraints. Let's go ahead and put them into a form that's easy to put into the equation editor on your calculator. So first off here we'll say y is greater than equal to 5,400 minus 60x all divided by 300, and this other y is greater than equal to 4,000 minus 80x divided by 80. You don't really need to worry about simplifying those. You could put those into the calculator as is. And again, these restrict us to the first quadrant, so we'll just put that into the window so we don't see the rest of the plane. We only see that first quadrant. All right, let's get our shading fixed. We want to shade above because we want y to be greater than, and then we can put our function in there. There we go. And then this one, again, we want to shade above, so fix the shading on that and then enter your function. And alpha y equals, we'll put 4,000 minus 80x, and that's over 80. There we go. And as far as how to set the window, it's easy for us to find x and y intercepts on these. And the only reason to do that would be for us to figure out the bounds of the window. So if we want to find the x-intercept, then we would get rid of the y, make the y 0. So home screen, 5,400 divided by 60. And we'd have 90. So that's 90, 0. And y-intercept, we would make the x 0, and that gives us 5,400 divided by 300, 18. Okay, and x and y intercepts here. Just take the 4,000 and divide it by 80. So x-intercept, I'm going to have 50, 0, and on the y-intercept, I'll have 0, 50. Okay, now how do you use this on your window? Well, we know that the x-min and x-min and the y-min are both going to be 0 because of these constraints here. The biggest x that I see is a 90, so we can put a 90 there. And the biggest y value that we see is 50. So we can put a 50 for the y max and graph. And you'll get a nice view of that region. We only have 3 corner points, here, here, and here, and it goes out and always past that. So we need to find those corner points in order to test them and see which is going to optimize our objective function. Okay, so let's calculate the intersection of those two boundary lines. We have 40 and 10. So 40 and 10. And then I'll calculate the 0 of, yes, we're headed towards this one. So left bound and right bound. Wait until the y becomes negative. And there we go. Enter. And it's 90, 0, which is exactly what we found there. Okay, 90, 0. And then we can trace. I want to make sure we're tracing the correct thing. And there we go, we're on that. So we go ahead and hit 0, enter, and we get 0, 50, which is exactly what we found over here. Only the 3 corner points. And now we'll put this into the objective function, each one of those, to see what the cost would be separating the hours out like this. So this is going to be 2,000 times 40 plus 3,000 times 10, and that would give us an operating cost of 110,000. And then I have 90 times 2,000. That would give us 180,000. And then 50 times 3,000. We get 150,000. So remember, for us to optimize our objective function, we are wanting to find the minimum to minimize the cost. So that would be 40 hours. Number of hours for plant 1 is 40 hours. Number of hours for plant 2 is 10 hours. And the minimum cost is going to be $110,000. Example 3, maximizing profit. Smoker Meatpacking Company makes 2 different types of hot dogs, regular and all beef. Each pound of all beef hot dogs requires 0.8 pounds of beef and 0.2 pounds of spices. And each pound of regular hot dogs requires 0.3 pounds of beef and 0.2 pounds of spices. And the remainder is made up of non-beef meat products. The company has at most 1,020 pounds of beef and has at most 5,000 pounds of spices available for hot dogs. How many of each type should be produced to maximize the profit? So the first thing that we are going to want to do is to identify what our variables represent. What are we going to let x and y equal? Well, what is it that we're dealing with? We are dealing with the number of hot dogs, either all beef or regular hot dogs, and we want to know how many of each we should make. We'll end up with an objective function that represents our profit, and that's what we'll optimize. But for our constraints, we're talking about the number of pounds of the all beef hot dogs and the number of pounds of regular hot dogs that we're going to produce, because that's what they've asked of us. We also have spices going on here, but we're not talking about producing spices. That's the materials that's going into this product. So let's separate our constraints into how many pounds of beef is used and how many pounds of spices is used. So first constraint on beef, we have 0.8 pounds of beef per pound of beef hot dog, the all beef hot dog. And then how much beef is in the regular hot dog. The regular hot dog requires 0.3 pounds of beef, so that's going to be 0.3 times however many pounds of regular hot dogs that you produce. And the constraint on beef is that we have at most 1,020 pounds of beef. So we're going to have less than or equal to 1,020 as your total for those. And then have a spices constraint, because that is also constraining. We have 0.2 pounds of spices for the all beef. So 0.2 pounds of spices goes into every pound that we produce, and then 0.2 pounds of spices for the regular hot dogs. So that's going to be 0.2 times every pound of the regular hot dogs that you produce. And remember, we have at most 500 pounds of spices. So this will have to be less than or equal to 500. And it's worth mentioning that we have x greater than or equal to 0 and y greater than or equal to 0. We're not going to be producing a negative number of pounds of hot dogs in the all beef or the regular. So this again just limits us to that first quadrant, and you don't need to actually graph these in your graphing calculator. It just kind of muddies it up a bit. So now we want to look at what kind of an objective function that we want. Remember, the objective function is the thing that you're going to optimize. In this case, we are maximizing the profit. So we need a profit function. What is your profit? Well, it says the profit is 90 cents on each pound of all beef hot dogs. So the profit from just the all beef hot dogs is going to be 0.9 times however many pounds of those all beef hot dogs you produce, and $1.20 on each pound of regular hot dogs. So that's going to be 1.2 times however many pounds of regular hot dogs you produce. Let's go ahead and get these constraints here into the right form to put into our equation editor. We're going to have y is less than or equal to 1,020 minus 0.8x, all divided by 0.3. And here, y is less than or equal to 500 minus 0.2x, all divided by 0.2. Get those entered into the calculator. My shading I need to fix. I want to be shading below this time. Y is less than. And put the function in. And here again, I need to fix my shading. I want to shade below. So there we go. And let's get our 500 minus 0.2x and divide that by 0.2. Double check and make sure you didn't make any errors entering that in. All right, let's look at what kind of numbers we should be putting in the window. If I find the x-intercept and y-intercept of these, it should help us with figuring out a good window. You can always just guess at these things too and just keep changing your zoom in and out and change your windows if you like. This is more of a definitive way to set that window from the get-go. See, 1020, if we're finding the x-intercept, we make the y0, so we're going to divide by 0.8. That's 1275, so 1275 comma 0. And y-intercept, we make the x0, so it'd be 1020 divided by 0.3, and that's 3,400. And here I have 500 divided by 0.2. That'll give me a 2500, 0, and 0, 2500. So when we're looking at the windows, the highest x value I have is 2500, and the highest y value that I have is 3,400, and then we can fine tune after that if you want to do that. We can see this is the area that's the feasible region. Anything in here is going to be a combination that satisfies the problem, but we want to optimize that. So we're going to try and maximize this profit function. Let's go ahead and do that. We'll find the corner points and then put that into the profit function to see what gives us the highest number. So we're going to calculate the intersection of those boundaries. I get 540 and 1,960. And again, let's calculate the 0. Make sure that we're tracing, yes, we're tracing the correct thing. So here, enter, and then right bound, enter, enter, and I get 1,275 comma 0, which is exactly what we got here. And then this, we can hit trace. Let's trace that one, hit 0, enter, and I get 0, 2,500, and I know that I have 0, 0 as my other boundary here. So if I put these into my objective function, I get here 2,838. Yeah, that's the profit there. And if I do it here, I get 1,275 times 0.9, and that'd be $1,147.50. Round that appropriately, show 2 decimal places. 2,500 times 1.2, and that may be surprising, $3,000. And of course, this is going to give a profit of $0. All right, so we have looks like we have a winner here at 0, 2,500. How do we interpret that? Means for the all beef hot dogs, we should be making 0 pounds and making 2,500 pounds of the regular hot dogs. Example 4, manufacturing. A company manufactures air conditioning units and heat pumps at its factories in Atlanta, Georgia and Newark, New Jersey. The Atlanta plant can produce no more than 1,000 items per day, and the number of air conditioning units cannot exceed 100 more than half the number of heat pumps. The Newark plant can produce no more than 850 units per day. The profit on each air conditioning unit is $400 at the Atlanta plant and $390 at the Newark plant. The profit on each heat pump is $200 at the Atlanta plant and $215 at the Newark plant. Suppose there is an order for 500 air conditioning units and 750 heat pumps. What we're going to do is make a system of constraints and graph that feasible region. We'll identify the corners, and then we want to make a profit function that we will then optimize. In this case, we'll be finding the maximum for it. What are we going to let x equal and y equal? Okay, the deal with this is that we have two different types of units being produced by two different factory locations. So we have to be pretty specific with this. We're going to let x equal the number of units, and we need to say AC units, number of AC units that are going to be coming from the Atlanta plant. And we know that if we have this order of 500 air conditioning units, then the number of AC units that are going to come from the Newark plant is going to be 500 minus however many the Atlanta plant is taking care of. Y will let be the number of heat pump units from Atlanta, and our order has 750 heat pumps ordered, so the number of heat pump units from Newark is going to be 750 minus however many heat pumps were produced by the Atlanta plant. Okay, so now we can start working on our constraints. Those are the things that sound like limitations. We see the first one here, the Atlanta plant can produce no more than 1,000 items per day. That's constraining. So we have here the number of units of AC that they produce plus the number of units they produce of the heat pump. Add those together, it can be no more than 1,000 per day. So it has to be less than or equal to 1,000. And then I have the number of, this is still pertaining to the Atlanta plant, that the number of air conditioning units cannot exceed 100 more than half the number of heat pumps. So that's going to be the number of AC units cannot exceed, so it has to be less than or equal to 100 more than half the number of heat pumps that are produced. And then we have the Newark plant can produce no more than 850 units per day. So that means if we add up the number of AC units and the number of heat pump units that are made in Newark, then it's going to be less than or equal to 850. Cannot exceed that 850 units per day. So we have three constraints here, and we'll go ahead and get those graphed and find the corners. That's part A of the problem. So let's get these in the right shape to do that. In order to put it into our equation editor, we're going to solve these for y so that they're in function form. Oh, I am missing my variable here. Okay, somehow it got erased. So I have y. I really don't like the fraction on that, so what I'm going to do is multiply everything through by 2 in order to get rid of that. And if I isolate my y, it would be a 2x minus 200 less than or equal to y. And I flip that whole thing around, it'll be y greater than or equal to 2x minus 200. And then this one, we can also simplify that quite a bit. That'd be 1250 minus x minus y is less than or equal to 850. Let's subtract 1250 from both sides and add x to both sides. So I have negative y less than or equal to negative 400 plus x. Divide or multiply both sides by negative 1 and it flips the inequality sign. So I have y greater than or equal to 400 minus x. So again, putting these all in one nice place to get into the calculator. And here we go. Go to the equation editor. Let's fix the shading first. We want to shade on this one below. And the inequality will be 1000 minus x. And second inequality, I'm going to shade above. There we go. Y is greater than. And that'll be 2x minus 200. 2x minus 200. And then y3, I'm going to shade above. So there we go. Y is going to be greater than or equal to 400 minus x. 400 minus x. And on the window, I know that my units are going to be greater than or equal to 0. I wouldn't be able to produce negative number of units. But x max, let's see, looks like the highest x could go would be 1000. So I'll just make the x max 1000. And the highest the y could be is 1000. So, and we'll graph that. And we can see the feasible area now in that window. We'll go ahead and pull that over. We want to try and find the corner points. So here we go on the calculator. We're going to calculate the intersection between y1 and y2. I get 400, 600. And then calculate the intersection between y2 and y3. And that's 200, 200. And then I'll do some tracing here. Just do trace, hit 0, enter, that's 0, 1000. And then trace again, except we want to be on y3. Go ahead and hit 0, enter, lands on that 0, 400. Okay, so those are the corner points of the feasible region. What we need to do is now optimize this. We have information on the profit that can be made. So the profit on each AC unit is $400 in Atlanta and $390 at Newark. So we can do profit for just the AC and then profit for heat pump and put it all together, be our total profit. That's where that information is coming from. So our profit is $400 times however many AC units are produced in Atlanta, and 390 times however many AC units are produced in Newark, 500 minus X, and $200 times the number of heat pump units produced in Atlanta, and $215 times the number of units produced in Newark, which is 750 minus y. And then we can simplify that. Definitely want to simplify that before we start plugging in these points. So P is 400x plus, let's put this into the calculator, 390 times 500, and that's 195,000. 195,000 minus 390x plus 200y plus 215 times 750, 161,250, and move this guy out of the way, minus 215y. Continue simplifying, just get our like terms together. That give us a 10x minus 15y and plus, so when I add up those two numbers I calculated there, 356,250. All right, so let's get the profit made with these different combinations of units made from each plant. So it'd be 10 times 400 plus, let's make it a minus, minus 15 times the 600 and add 356,250, and this would give me 351,250 as a profit. Let's try the 0.200, 200. And what I can do here is just copy my function from before. I replace the 400 and 600 with 200s, and I get $355,250 profit. And then we can do that again if you want to just copy and make this a 0 and make this 1,000. We'll have to insert a 0. So that'd be 341,250. And again, go back up and copy. We've got 0 and 400. And that would be 350,250. And the looks like the highest profit we will make is this. So it'll be 200 units of AC units from Atlanta and 200 heat pump units from Atlanta. Remember, we had an order for 500, so that's going to be 300 AC units from Newark and 550 units of heat pump from Newark. And that maximum profit is going to be $355,250. That does it for that section, and just let me know if you have any questions on it.